New mathematical tools are being created to deal with the conflicting demands of minimizing structural weight and cost while maximizing performance to attack complex problems involving interrelated solid mechanics and unsteady aerodynamics. Sophisticated computer programs allow the user to interact with and modify the design under study. The nation's largest center of military aerospace research and development is located at Wright-Patterson Air Force Base, Ohio. And one of the major organizations here is the Air Force Wright Aeronautical Laboratories, or AFWAL. This organization includes 4 laboratories which develop Air Force-relevant advanced flight dynamics, aeropropulsion, avionics, and materials-related technologies. To carry out its mission, AFWAL employs nearly 2,800 people and operates on an annual budget currently exceeding $500 million. Replacement cost of the laboratories, their facilities, and equipment is estimated at $750 million. A major portion of AFWAL's work is conducted by industry and institutions of higher learning. An aggressive in-house program exploits new opportunities, maintains technical expertise, and verifies contractor findings. AFWAL is active in all phases of R&D, conducting basic research, exploratory development, and advanced development programs in many fields. It is also responsible for assigned engineering development efforts and for the Air Force Manufacturing Technology Program. In addition to developing the technology needed for future Air Force systems, AFWAL supports the product divisions of the Air Force Systems Command in the acquisition of new systems and in resolving developmental and operational problems. AFWAL is involved in nearly every aspect of flight vehicle technology, from the materials and structures that hold the system together, to the engines that propel it, to the avionics that control and guide it. New concepts in aerodynamics are studied mathematically, often with the help of the computer. This, for example, is how airflow over a wing changes with increasing angle of attack. Lift and drag can be accurately predicted, reducing the need for expensive wind tunnel tests. Advances in analytical techniques and computational capabilities may someday make it possible to accurately predict the aerodynamics of an entire vehicle throughout its full flight envelope. Theoretical predictions are verified through wind tunnel tests of scale models, like this concept for a high-speed fighter. Its parasol wing interacts with the shock wave generated by the airplane's nose. This design increases the wing's aerodynamic efficiency, thereby reducing drag and extending aircraft range. Tests like this, which simulate the conditions expected in flight, are essential in determining the performance characteristics of new designs. New mathematical tools are being created to deal with the conflicting demands of minimizing structural weight and cost while maximizing performance. These tools are used to attack complex problems involving interrelated solid mechanics aeroelasticity, and unsteady aerodynamics. Sophisticated computer programs allow the user to interact with and modify the design under study. These new analytical tools are complemented by improved methods of determining the response of complex structures in static, dynamic, and thermal load environments. These tests, for example, assess the aeroelastic response of an airplane wing. Improvements in structural design are being matched by the application of new materials. New composites, because of their high strength and stiffness characteristics, promise significant weight reductions in future aircraft at comparable or lower acquisition costs than today's materials. Because of their inherent resistance to corrosion and fatigue, they also promise longer service life and lower operating costs. In parallel with materials development is a broad program to develop the manufacturing methods needed to exploit them. Laser machining, for example, is a space-age breakthrough in precision production methods. Directed by automatic numerical controls, a laser beam requires only minimal tooling and can cut tough materials like titanium with essentially no equipment wear. New technology requires extensive verification before it's ready for transition to further development. In AFWAL, this activity ranges from relatively simple laboratory experiments to tests of complete aerospace systems. The structural test facility is unique in the Department of Defense. Its activities range from evaluating the fracture and fatigue characteristics of new joining techniques to full-scale static and fatigue testing of complete aerospace vehicles. Evaluations are carried out at temperatures ranging from cryogenic to those typical of flight at several times the speed of sound. 5 computers are required to handle the 2,000 channels of data needed in a typical test, such as in this recent fatigue test of a full-scale wing carry-through structure, which failed at 125% of design load. AFWAL also has the most modern sea-level engine test facility in the Air Force, capable of handling engines of up to 60,000 pounds of thrust. A computer directly controls the facility and its various test, safety, and operating systems. Accelerated mission tests duplicate in a few hundred hours the wear and tear that an engine would normally experience during years of operational service. This is part of a broad program aimed at developing the technology needed to improve the durability of future turbine engines. AFWAL programs are developing economical ways of finding structural defects before they become a problem. Ultrasonics, for example, can be used to detect cracks in engine discs, while rotating eddy current probes can be used to look for cracks inside bolt holes. Concepts like these will someday allow expensive parts to be retired for cause, rather than because they have reached some predetermined age limit. Future engines will have far fewer parts and will be far more durable than those now in use. Promising new components like these are incorporated into advanced gas generators for demonstration in a realistic engine environment. This is vital because turbine engines are among the most highly stressed of all aircraft subsystems. Some engine components must operate at temperatures well over 2,000 degrees Fahrenheit, with internal pressures exceeding 400 pounds per square inch. Stresses of up to 60 tons per square inch are experienced in those components rotating at 10,000 revolutions per minute. Testing a new gas generator requires hundreds of channels of instrumentation to measure the many parameters that characterize its operation. Proven gas generators are serving as the cores of advanced technology demonstrator engines being developed jointly with the Navy. These range from small turbofan engines for future trainers to large variable cycle afterburning engines whose performance can be optimized in flight for each part of the mission envelope. Compared to current operational systems, they offer reduced fuel consumption, better performance, and fewer parts, all of which contribute to more reliable, more maintainable, and more economical Air Force systems. AFWAL is now operating the first facility capable of testing turbine engine compressors under controlled transient conditions. The 30,000 horsepower facility provides the realistic steady state and dynamic test conditions needed to assess the influence of engine speed changes, afterburner ignition, and airflow distortion on compressor performance and stability. Improvements in engine and airframe efficiency are two steps being taken to meet the nation's energy goals. Approaches are also being explored to increase the supply of aviation fuel while holding down costs. By relaxing specification requirements, for example, less expensive fuels can be used. To reduce Air Force reliance on foreign sources of oil, AFWAL researchers are also assessing the qualities of aviation fuels derived from domestic non-petroleum resources, such as oil shale, coal, and tar sands. Current work is aimed at developing an understanding of the complex relationships between fuel characteristics and system performance, durability, emissions, survivability, and cost. New concepts of computer-aided manufacturing will integrate all aspects of design and production, drastically reducing the cost of conventional methods. Processes like isothermal forging are producing parts that require very little machining, reducing both labor cost and material waste. Developing flight control systems involves designing the aircraft, measuring its motions, the hardware and computers needed to control these motions, understanding the pilot's needs, and designing the flight deck with its controls and displays. A unique simulator facility gives AFWAL the capability to fly virtually any conceivable flight vehicle before it's built. It duplicates maneuvering loads on the pilot and the in-flight cockpit environment, including gunfire and engine noises. Images are projected on a screen in front of the single-seat cockpit. New concepts in flight control are being developed from previous work in digital controls and fly-by-wire technology. These concepts, which include this control configured vehicle, emphasize extensive integration of flight control with other vehicle subsystems, including propulsion, fire control, navigation, and crew. Future aircraft will be able to translate sideways without rolling, move vertically without pitching, and quickly change their forward airspeed. Pilots may even be able to change the contour of their aircraft's wings in flight, thereby optimizing their shape for specific phases of the mission. Dramatic improvements in combat effectiveness will result. In air-to-air engagements, an earlier chance to fire with more hits through firing opportunities with greater accuracy. In ground attack, more accurate delivery of weapons, and a better chance to avoid hostile fire. AFWAL technology will make future aircraft more survivable in combat and safer to operate in peacetime. This facility, which simulates aircraft combat damage effects, is used to test new protection techniques and to study the damage caused by projectiles and warhead fragments on aircraft flying at speeds over 500 knots. Laboratory researchers are also learning how to counter advanced threats. This laser can put 15 kilowatts of focused energy on a target. The beam passes through a wind tunnel which allows accurate engagement simulations for aircraft flying at several times the speed of sound. Combat aircraft must be able to operate in an increasingly sophisticated electronic environment. This unique in-house facility permits the evaluation of new electronic warfare equipment and techniques under realistic conditions. One of its two simulators generates a dense, dynamic, multi-signal radar background environment for evaluating radar homing, warning, and electronic intelligence receivers. The other simulator is used to evaluate the effects of electronic countermeasures against a generically represented threat radar. The simulators can be used together to evaluate the most modern ECM systems. Threats, of course, take different forms. Simply surviving in the flight environment often requires advanced materials and protective coatings as used in new radome materials undergoing thermal pulse testing. Even birds represent threats to low-flying aircraft. New designs and materials for canopies and windshields are being developed and tested to reduce the damage from bird impacts. One way to reduce the number of air crews required for combat is to use unmanned systems for some missions. This ultra-low-cost, remotely piloted vehicle, developed in-house, can fly at 100 knots carrying a 100-pound payload and stay aloft for 8 hours. Extensive use of non-metallic materials like foams and fiberglass holds cost and weight to a minimum. The mini RPV can carry a variety of sensors, experimental equipment, target designators, and warheads. AFWAL has a major technology program for future air-launched cruise missiles. New concepts in turbine engines promise significant reductions in fuel consumption, especially important since greater missile range reduces the distance that launch aircraft must penetrate enemy defenses. Range is directly proportional to recoverable fuel energy per gallon. The high energy density of the special fuel AFWAL developed for this outcome increased its range by more than 15%. More exotic fuels based on boron and carbon promise even higher energy and greater range. Similar fuels were developed for a ramjet-powered supersonic cruise missile demonstration program. Compared to rockets, ramjets offer greater range, higher average speed, and retain maneuvering thrust all the way to distant targets. To keep pace with the additional range and longer flight times made possible by variable geometry inlets and nozzles, AFWAL is developing more durable combustors, some made of advanced composite materials that can withstand the severe environment. Ramjet propulsion is now ready for application to air-launched tactical missiles. Improved speed, range, and maneuverability can greatly enhance kill capabilities against both aerial and ground targets. This facility is used to evaluate the jamming susceptibility of infrared seekers used in U.S. and foreign missiles. The system includes a simulated target aircraft as well as jammer and decoy sources which interact with the seeker hardware. A computer simulates homing interceptions of the target. Varying the intensities of jamming signals produced by lasers or heat sources can confuse the seeker. Advanced technology is also being developed to meet the needs of future re-entry vehicles. This composite nose tip withstood 7,000 degree Fahrenheit temperature and 80 atmospheres pressure during simulated re-entry. It demonstrated low ablation and proved resistant to cracking, nuclear effects, and erosion. AFWAL's space technology involvement also covers structures, coatings, and electrical power supplies. The primary power source aboard most long-lived satellites is an array of solar cells which convert sunlight into electricity. Current work emphasizes hardening the cells to withstand nuclear weapon and laser radiation effects. Emphasis is placed on developing solar cells with improved efficiency to reduce the weight and cost of the cells needed for a satellite. This work is complemented by the development of new concepts for lightweight storage cells needed in satellite power systems for those periods when the satellite passes into the Earth's shadow. Prototype navigational equipment designed for use with the Navstar satellites of the Global Positioning System is evaluated in this facility. The computer-controlled simulator is easily adaptable to customer requirements and can exactly duplicate mission scenarios. It offers manufacturers and users a practical alternative to expensive field tests. The AFWAL mission spans a broad range of technical functions. Laboratory goals are both systems and technology-driven. Many aerospace technologies are matured by large-scale integrated demonstrations which provide proven options for future systems. The AFWAL concept is a dynamic approach to advancing technologies that cross over many disciplines. Whether solving current Air Force problems, meeting operational needs, or laying the technology foundations for future aerospace vehicles, AFWAL will continue to make major contributions in solving problems and reducing the ever-increasing complexities of national defense. AFWAL combines highly competent people, nationally unique research facilities, and a multi-million-dollar budget in a vital, energetic organization dedicated to the needs of the Air Force and the security of the nation.